Hello, I am Manas and our project is based on DNA compression techniques. So let's go over the abstract of our project. With rapid expansion of genomic data driven by next generation sequencing NGS, now we face major challenges in how we store, transmit and analyze our data efficiently. In this project, we explore modern DNA specific compression techniques that move beyond traditional general purpose methods. These new approaches take advantage of the repetitive and standard structure of DNA sequences. We examine both classic methods like Huffman encoding as well as run length encoding, etc., and more advanced transformer based deep learning models as well. Our goal is to find the right balance between compression ratio, speed, and accuracy, ensuring these methods can be integrated into today's bioinformatics pipelines. By blending traditional algorithms with machine learning, this project aims to build a more intelligent and scalable solution for managing massive genomic datasets. So modern DNA sequencing technologies are generating data at an unprecedented scale. So to put into perspective, a single human genome contains around 3 billion base pairs and NGS is producing petabytes of data each year. So 1 petabyte is like 1000 terabytes, that is equivalent to 1000 hard drives, right? So traditional compression tools like GZIP or BZIP2 were not designed with this kind of biological data in mind. So DNA has only 4 nucleotide bases, right? So A, T, G and C. Its features contain repetitive patterns and structured regions that the general purpose compressors simply don't exploit. This mismatch has created a critical bottleneck. The massive volume of data is now a major challenge, not just for storage and transmission, but also for efficient downstream analysis, especially in large-scale research and clinical genomics. Now let's get into challenges and opportunities. The rate at which DNA data is being generated is staggering thanks to the rapidly falling sequencing costs dropping even faster than Moore's law. Repositories like Sequence Read Archive now hold over 45 petabytes of data and are doubling roughly every 18 months. This is not sustainable. Even top tier research institutions are feeling the pressure, and in lower resource settings, storage becomes a serious barrier to progress. But storage is only part of the problem. Transferring these massive uncompressed datasets causes real bottlenecks in collaboration and scientific discovery. And when it comes to computation, the larger the data, the slower and more resource intensive the analysis. That said, there's a powerful opportunity here. Compression doesn't have just to shrink data, it can help us understand it. Smart compression techniques can explore biological patterns like repeats and motifs, giving us insight while reducing the file size. That's the goal of this project, to design compression methods tailored for DNA, from classic algorithms like Huffman and run length encoding to cutting edge transformer based models. The aim is clear: reduce storage burden without compromising biological value. Let's get into the objectives of this project. First, we aim to design specialized compression algorithms tailored specifically for DNA. This includes implementing methods like Hoffman coding, run length encoding, and transformer based models to outperform the general purpose tools like GZIP and BZIP2. Second, we plan to harness the power of transform models by training lightweight architectures on Kramer tokenized sequences. These models will learn compact and biologically meaningful representations for intelligent compression. Third, we will develop an efficient compression framework that ensures fast encoding and decoding while preserving sequence integrity. This will also support random access to specific genomic regions. Fourth, we will evaluate the performance trade-offs, analyzing compression ratio, speed, and memory usage across a wide variety of datasets, including whole genomes, exomes, RNA sequences, and metagenomes. Fifth, we aim for seamless integrations with existing bioinformatics workflows by supporting standard formats like FASTA or FASTQ, ensuring compatibility with common downstream tools. Our sixth objective is to explore whether transformer-based compression can reveal biologically relevant patterns such as motifs or structured features that traditional methods may miss. Finally, we compare rule-based and machine learning-based approaches to understand their respective strengths and weaknesses, especially when dealing with complex or high repetitive genomic regions. Now let's look into the current DNA sequence compression scene. DNA may look simple on the surface, right? Just 4 nucleotide bases A, T, G and C. This limited alphabet makes it seem like an ideal candidate for compression, but reality is far more complex. Biologically, sequences contain patterns like repeats, structural motifs, and significant variation, of all of which is a complicated compression. Traditional tools like gzip and bzip2 treat DNA as ordinary text. They ignore these biological patterns, offering limited compression performance. They also lack features like random access and provide no insight into the underlying biological information. Moreover, DNA is rich in complex structures, tandem repeats, palindromes, GC-rich regions, and conserved domains, none of which are recognized by generic algorithms. That's why specialized methods matter. Effective DNA compression isn't about shrinking file size, it's about understanding and modeling the biological structure to improve how we store, access, analyze this data. Now let's take a look at the existing approaches. Reference-based approaches like CRAM store only differences known as reference genome. These work well when the reference is close, but they struggle with novel or noisy data. Statistical and dictionary-based tools such as DNA Compress and Leon reduce redundancy by modeling sequence patterns or using dictionaries. While they achieve moderate compensation, typically 4 to 6 times, they can be slow and lack flexibility. Transform-based techniques, including using the Burrows-Wheeler transforms or wavelets, allow for faster indexing but still rely on relatively simple sequencing features. Then we have machine learning-based methods. Transformers and other deep learning models can learn much richer, much complex patterns, enabling vector-based and potentially more generalizable compression. But here's the catch. No current method achieves the best perfect balance compression efficiency, biological accuracy, speed, or seamless integration into existing bioinformatics frameworks. This unmet need is exactly what our project aims to address. Huffman coding. Huffman coding is one of the most well-known lossless compression algorithms, and it works especially well with DNA. Since DNA contains only 4 characters A, T, G and C, there is a lot of potential to reduce file size by assigning shorter binary codes to more frequently occurring bases or patterns. Here's how it works. First, we calculate the frequency of each nucleotide or chimer. Short subsequences of DNA. Chimers are short subsequences of DNA. Next, we build a binary tree here where the most frequent patterns get the shortest binary codes. Using this tree, we can encode the DNA into a compressed binary format. For decompression, we simply reverse the process using the same tree to reconstruct the original sequence as it exactly was. Huffman encoding is straightforward, dependable, and most importantly, lossless. That makes it a strong choice for compressing biological data to formats like FASTA or FASTQ, where data integrity is crucial. For this, we use tools like Python for scripting, NumPy for efficient data handling, and BioPython to parse DNA sequence files. Run length encoding, or RLE, is another simple yet powerful technique for compressing DNA sequences. It works by identifying repeated nucleotides and replacing them with a single character followed by the number of repetitions. So, for instance, if the sequence is AAAAAA, it becomes A6. The algorithm scans the DNA sequence from left to right, and whenever it encounters a run of the same nucleotide, it compresses that stretch into a more compact form. This method is particularly effective in regions with long repetitive sequences like telomeres, which often contain repeats of TTA, GGG, or microsatellites. RLE stands out because it is lightweight, fast, and extremely easy to implement and decode. It's especially useful in genomic regions where the repetition is abundant. However, we have to note its limitations. RLE doesn't perform well on sequences without long repeats, and its compression efficiency depends heavily on the structure of the input data. In our project, we implement RLE using Python and NumPy to handle sequence data efficiently. Now let's look into transformer-based compression. This method takes a modern approach to DNA compression by leveraging transformer-based deep learning models. These models are capable of learning intricate patterns and biological structures in the DNA sequence. patterns that the traditional compression methods often overlook. The process begins by breaking the DNA sequence into kmers, short subsequences like 6mers, example ATC GGA. These kmers are then fed into a transformer model which learns to represent them as dense vector embeddings. Instead of storing the raw sequence, we only store the compressed embeddings, significantly reducing the data size. The great thing about this method is its flexibility. Depending upon the storage needs, the embeddings can be used for either lossless reconstruction or lossy compression, offering a balance between size and data fidelity. Why is it important? Transformer-based compression can outperform traditional methods like GZIP or BZIP2, especially in regions of the genome that are complex or highly variable. Additionally, these models learn biologically relevant features from the data, potentially revealing insights that the other methods miss. This approach also opens up possibility for integration with omic datasets such as RNA or protein sequences. For implementation, we use Python, PyTorch, TensorFlow for model training, and Hugging Face transformers for model architecture and utilities. Now let's take a look at the current status of our project. So we have implemented Huffman encoding, and the results can be seen in the bottom right corner. So we achieved around 40% compression ratio, and we tested these sequences in the 3 genomes from human mitochondrial complete genome. So from those we chose 3 sequences and we tested them, and we achieved a 40% compression ratio. And it does not take that much time for encoding and decoding well compared to other methods. And the drawbacks are, for certain nucleotides like NRYS, it might get stored in the FASTQ and FASTA and FASTQ files. They might get ambiguous. That is, when it exceeds a particular limit, the complexity increases and the compression ratio might get worse. For RLE, instead of the general approach where a numerical pair and nucleotide will have both 8 bits, instead of that, what we did is we took a mapping for the ambiguous nucleotides. So there are like 8 ambiguous nucleotides, then there is 3 bits for mapping, and the integer won't cross above 9. So it is 4 plus 3, 7 bits instead of the 16 bits, which highly increased our scores. So the compression ratio was average around 60%, but the time for encoding and decoding is much higher. That is the drawback for RLE. So LZW is another dictionary approach, and this compared to others takes a little bit more time in the encoding, whereas in decoding you have the mapping already with you. So decoding time is very low, but the encoding time is much higher. Scores are better than Huffman. So in summary, we have implemented Huffman RLE and LCW along with early work on transform based compression. On going forward, we aim to integrate Hugging Face tools and to scale to larger datasets and explore lossy compression and also multi-omics integrations. Thank you.